Welcome to Podcast Learn and Fun. Let's start today's journey of learning. Okay, so today we're going to be talking about matrices. Have you ever heard of a matrix? Like, not the movie, but in math.
Yeah, they're kind of like spreadsheets, just rows and columns of numbers. You use them to represent all sorts of data, like from images to financial markets to the very fabric of space-time.
Whoa, space-time. That sounds pretty intense. But okay, so let's say we have a matrix. Is there anything special about the numbers inside, like any patterns or calculations we can do with them?
Absolutely. One of the simplest yet most fascinating calculations you can do with a matrix is finding its trace.
Okay, so how do you find the trace? Is it some crazy formula?
Nope, it's actually super easy. You just add up the numbers. Along the main diagonal,
Wow.
from the top left corner to the bottom right corner.
Huh, that doesn't sound too bad. So what's so special about this trace thing?
Well, what's really interesting is that even if you change the basis of the matrix, the trace stays the same.
Hey, what do you mean by changing the basis? Is it like converting miles to kilometers? But for matrices.
It's a bit like that. Imagine you have a map of a city. You could use different coordinate systems to describe locations on that map. You could use street names and numbers, or you could use latitude and longitude. The map itself doesn't change, just the way you describe the points on it. It's the same with matrices.
Okay, I think I'm following. So even if you change how you're looking at the data in the matrix, the trace stays the same. Why is that? What makes it so special?
That's where eigenvalues come in. They are deeply connected to the trace.
Eigenvalues, okay, now you're just using big words to scare me.
Yeah.
What in the world are eigenvalues?
Imagine you have a rubber band and you stretch it. The direction it's stretched is like an eigenvector, and how much it's stretched is like an eigenvalue.
Okay, I can kind of picture that. But how do rubber bands and stretching relate to matrices in this whole trace thing?
Think of the matrix as a transformation, like stretching or compressing the rubber band. Eigenvalues tell you how much the matrix stretches or compresses things in specific directions.
So the trace is like a summary of all those stretchings and compressions.
Exactly. It tells you the overall effect of the matrix transformation, regardless of which direction you're looking at it from. That's why it stays the same even when you change the basis, because it's capturing something fundamental about the matrix itself.
Wow, that's pretty mind-blowing. This simple sum of numbers, the trace, is actually telling you something really deep about the way the matrix transforms things. But why should we care about any of this? Does this trace thing actually matter in the real world?
Oh, it matters a lot, actually. Take computer graphics, for example.
Okay, I love video games, so tell me more.
Let's say you're designing a 3D character for a game. You want to be able to rotate and move that character around the virtual world without their size or shape getting distorted.
Yeah, that would look super weird if their arms suddenly stretched out like Mr. Fantastic every time they turned around.
Exactly. And that's where the trace comes in. Because it's invariant under changes of basis, it can help ensure that the character's size and proportions stay consistent, no matter how they're positioned or rotated in the game.
So it's like a mathematical guardian, making sure the character always looks right. That's pretty cool. But computer graphics is just one thing. You mentioned that matrices can represent all sorts of data. Does the trace come in handy in other areas too?
Oh, absolutely. It pops up in fields like machine learning, physics, and even economics.
Wow. So it's not just about video games and pretty pictures. It sounds like the trace is kind of a big deal in a lot of different areas. Can you give me another example?
Sure. Let's talk about machine learning. Let's say you're training a computer to recognize different types of flowers.
Okay. So the computer needs to be able to tell a rose from a daisy, even if the picture is taken from different angles or in different lighting.
Exactly. And to do that, the computer needs to extract features from the images, like the shape of the petals or the arrangement of the leaves.
Right. Those features are what make each type of flower unique.
And the trace can help the computer focus on those invariant features, the ones that stay the same even if the lighting or the angle of the photo changes. It helps the computer see past the irrelevant variations and identify the core characteristics of the flower.
That's amazing. So it's like the trace is giving the computer a superpower, helping it see the forest for the trees.
That's a great way to put it. The trace helps us uncover the hidden patterns and connections in data, and that's incredibly powerful.
So this simple little calculation, the trace, is actually a key to understanding all sorts of complex systems.
Yeah.
I'm starting to think this whole matrix thing is pretty fascinating.
It is, and we've only just scratched the surface. The trace is just one piece of the puzzle, but it opens up a whole world of mathematical insights.
Okay, I'm officially hooked. What else can you tell me about matrices and the amazing things they can do? Okay, so We've talked about computer graphics and machine learning. Where else does this idea of the trace being invariant come in handy?
Well, think about designing a bridge. The bridge needs to be strong enough to handle all sorts of forces and stresses, like wind traffic, even earthquakes.
Right, you don't want the bridge collapsing at the first sign of trouble.
Exactly. And engineers use mathematical models to make sure the bridge is stable and can withstand those forces.
And I'm guessing those mathematical models involve matrices.
You bet. Matrices are great at representing complex systems, like bridges. And the trace, because it's invariant, helps engineers ensure that the bridge's structure stays sound, even when things get a little shaky.
So the trace is like a mathematical safety net, making sure the bridge doesn't fall down.
It's more like a mathematical principle that guides the design process. By understanding how the trace behaves, engineers can build structures that are strong and resilient.
It's amazing how this seemingly simple concept, the sum of numbers along a diagonal, has such profound implications for the real world.
It really speaks to the power of mathematics, doesn't it? It's a language that allows us to understand and describe the hidden patterns of the universe.
I'm starting to see that. We started with a simple calculation of
Yeah.
the trace, and we've ended up talking about everything from video games to bridges to the fundamental nature of reality.
That's the beauty of exploration. You never know where a simple question might lead you.
Well, this has been an incredible journey. Thanks for taking me on this deep dive into the world of matrices and the fascinating invariance of the trace.
My pleasure.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.